Create a fast-paced video for YouTube about Unbersgang, the living knowledge graph, how AI agents will know what's happening right now. Hook. Imagine you have an AI agent. It has access to your company database. It can call APIs. It can read PDFs. It can search emails. It can look at your CRM. Sounds powerful, right? Now let me ask you something uncomfortable. What happens when all of that information changes 5 minutes after you gave it access? A customer changes their address. A payment fails. A shipment gets delayed. Someone uploads a new contract. An API reports a completely different status. And your AI agent, it's confidently reasoning from yesterday's information. That's not an intelligent agent. That's an intern with a 5-minute-old spreadsheet. And this is where something much bigger than RAG is emerging. The real-time knowledge graph. A system that doesn't just store knowledge, but continuously updates its understanding of the world. And today, I'm going to show you exactly how you build one. The problem with today's AI agents. Let's start with the way most AI applications work today. You have your data, maybe it's sitting in PostgreSQL, some of it is in Salesforce, some comes through APIs, you have a folder full of PDFs, maybe there are support tickets, emails, spreadsheets, basically, the beautiful mess that every real company calls data. Then somebody says, let's connect an LLM to all of it. So we build RAG, we chunk the documents, create embeddings, put them into a vector database, and when the user asks a question, we retrieve the most similar pieces of information. Great, except there's a fundamental problem. Similarity isn't the same thing as understanding. Suppose I ask, why did this customer's shipment get delayed? A vector search might find a document mentioning the customer. It might find a shipping policy. It might find a support ticket. But the real answer could require connecting 5 different systems: customer, order, warehouse, carrier, and a live API status. That's not just a document retrieval problem. That's a relationship problem, and that's exactly where graphs become powerful. What a knowledge graph actually does, don't let the phrase knowledge graph scare you. At its core, it's just a map of things and how those things are connected. Imagine, customer, placed, order, contains, product, manufactured by, company, supplied by, supplier, located in, country now. Suddenly your data has structure. Instead of asking, which document mentions this customer, you can ask, show me everything connected to this customer that could explain this event. That's a completely different way of thinking. And here's the part that matters for AI. LLMs are good at language. Graphs are good at relationships. Put them together, and you start getting something interesting. But there's a big problem. Here's the trap. People hear knowledge graph and think, okay, we'll build the graph once. No, that's exactly what we don't want, because the real world doesn't sit still. Your database changes, your APIs change, your customers change, your documents change, your inventory changes, your employees change, your relationships change. So a knowledge graph built once becomes stale, and a stale knowledge graph feeding an AI agent can actually be worse than having no graph at all, because the AI sounds confident. That's the dangerous part. Enter the living knowledge graph. What we really want is a graph that behaves more like a living system. Something like this: database changes, an event is generated, the graph updates, vector search updates if necessary. The AI agent sees the new state, the agent reasons, the agent acts, and this can happen continuously. Not every night, not once a week, continuously. That's the difference between a static knowledge graph and a living knowledge graph. Let's build one. Let's take a real example. Imagine we're building an AI customer support agent. Our company has 4 major sources of information. Source number 1, PostgreSQL. It contains customers, orders, payments, inventory, shipping information. Source number 2, APIs. Maybe the shipping carrier provides live tracking. Maybe a payment provider gives transaction status. Maybe a weather API tells us about disruptions. Source number 3, uploaded files, PDF contracts, invoices, product manuals, warranty documents. Source number 4, maybe events, customer support tickets, website activity, IoT sensors, whatever. So we've got this giant mess. Now we need to turn it into something an AI agent can actually reason over. Step 1. Ingest the data. The first layer is ingestion, and this is where people often make a mistake. They try to force every source into the same pipeline. Don't. Different sources behave differently. Your database might change every second. An API might provide webhooks. A PDF might appear once a day. A CSV might arrive every Monday. You need different ingestion mechanisms. For databases, you can use Change Data Capture, or CDC. Instead of constantly asking, did anything change? You capture changes as they happen. So imagine, PostgreSQL customer updates their address. CDC detects the change. An event is created, something like customer 123 updated address. That event enters your streaming layer, and now the rest of your system can react. Step 2. The event bus. This is where something like Kafka or Google PubSub becomes extremely useful. Think of it as the nervous system. Your data sources produce events. The event system distributes them. For example, order created, payment failed, customer updated, shipment delayed, new PDF uploaded, API status changed. These events flow through your architecture, and here's why that's powerful. You don't want your graph database constantly polling 10 different systems. You want changes to come to you. That's the difference between go check whether something changed and something changed. Here it is. Huge architectural difference. Step 3. Turn raw data into knowledge. Now comes the interesting part. An event says, customer 123 created order 456. That's useful, but the graph needs to understand what that means. We might create customer 123 connected to order 456 with the relationship placed, then order 456 might connect to product ABC with contains, and product ABC might connect to supplier XYZ with supplied by. Now we're building the graph. But there's another problem, and this one is nasty. Entity resolution. Suppose one system calls the company Microsoft Corporation, another says Microsoft, another says MSFT, and a PDF says Microsoft Corp. Are those 4 companies? No, they're one entity. If your system doesn't figure that out, you get 4 disconnected nodes, and suddenly your graph looks impressive, but it's wrong. This is why entity resolution is one of the most important pieces of a real knowledge graph. You need to determine, who is this? What is this? Is this the same entity we've already seen? And sometimes that's deterministic. Sometimes it's fuzzy matching. Sometimes you use machine learning or an LLM to help, but you need a canonical identity, because otherwise your graph becomes a junk drawer. Step 4. Don't put everything into the graph. Here's another mistake. Someone uploads a 300-page PDF, and they think, let's put the entire PDF into Neo4j. No, the graph isn't your filing cabinet. The graph should capture the important entities and relationships. For example, a contract might produce customer, A contract 123, product X renewal, date supplier Y, and relationships between them. But the actual paragraphs of the contract, those can live in your document vector layer. This gives us a much better architecture. Graph plus I use vector. And this is where GraphRAG gets interesting. You don't have to choose graph or vector database, you can use both. The vector system is good at find information that is semantically similar. The graph is good at show me how these things are connected. Now combine them. Suppose the user asks, why is customer 123's shipment delayed? The system might first identify customer 123, then traverse customer, order, warehouse, shipment, carrier, and at the same time perform vector retrieval over support tickets, contracts, shipping documents, emails. Then the AI receives both structured relationships plus unstructured evidence. Now we're cooking. Real time makes this much more powerful. Let's say the shipment was fine at 10 a.m. At 10:03, the carrier API reports severe weather delay. The API sends a webhook. The event enters the stream. The graph updates. Now the AI agent gets asked, what's happening with this shipment? It doesn't answer from yesterday's information. It sees current carrier status, delayed, reason, severe weather, customer contract, priority delivery, estimated arrival, tomorrow, and it can respond. The shipment is currently delayed because the carrier reported severe weather. The customer's contract includes priority shipping, so I've escalated the delay. That's a very different AI agent. It isn't simply retrieving documents, it's reasoning over a changing world. And this is where the database choice matters. Now let's revisit the technologies we talked about. If you're building this kind of system, you have several options. Neo4j Aura. This is probably where I'd start for a general-purpose GraphRAG system. You get a native graph database, strong graph traversal, cipher, and a mature ecosystem around knowledge graphs and AI. If your primary question is, how do I build a knowledge graph that an AI agent can reason over? Neo4j is a very natural starting point. Memgraph. Now suppose your entire application is obsessed with real-time events, fraud, cybersecurity, IoT, network monitoring, constantly changing relationships. That's where Memgraph becomes particularly interesting. The pitch is basically, don't just store the graph, process the graph as it changes. That's a very powerful idea. Spanner graph. Now let's say you're building something enormous. You need global distribution, transactional consistency, and graph capabilities. That's where Spanner graph becomes fascinating. Instead of having one database for transactions and another system for graphs, you're trying to bring those worlds together. For massive enterprise systems, that's a serious architectural advantage. Neptune. If you're already deep into AWS, Neptune becomes an obvious candidate. You get managed graph infrastructure inside the AWS ecosystem, and that can dramatically simplify the architecture for organizations already living in AWS. Sorry, TigerGraph. And if your problem is massive graph analytics, especially fraud, AML, network analysis, TigerGraph becomes extremely interesting. It's less, I'm building a simple knowledge graph, and more, I have an enormous network and I need to perform serious graph analytics on it. But what about Postgres? Here's where things get interesting. Maybe you don't need a graph database. Maybe you have a relatively small system. You already have PostgreSQL. You can extract relationships, use Network X, run graph algorithms. Done. That's completely reasonable for a prototype. But as your graph becomes central to the application, you eventually start asking, why am I constantly reconstructing the graph? And that's usually when native graph infrastructure starts making more sense. So what about AlloyDB plus PG Vector? This is a different category. AlloyDB plus PG Vector is much more naturally suited to relational data, plus semantic search. You might build PostgreSQL data, plus embeddings, plus vector search, and that's excellent for RAG. But if your application's core question becomes, traverse 6 levels of relationships across millions of entities, that's when I'd start looking at a native graph system. What about BigQuery? BigQuery is another interesting one. If your organization already has enormous analytical data sets, and you want to run graph analytics across them, BigQuery can be extremely attractive. But again, analytics is not the same thing as operational graph reasoning. If your AI agent needs to make a decision based on the graph right now, I'd generally favor a graph-oriented operational system. If you need to analyze massive historical datasets, BigQuery becomes extremely compelling. And here's the architecture I would build if I were designing this from scratch for an AI agent. I'd start with database, plus APIs, plus files, CDC, webhooks, file ingestion, Kafka or pub/sub, entity resolution plus transformation, Neo4j plus vector database, hybrid retrieval, LLM, agent, action, and notice something, the LLM is almost at the end. That's intentional, because here's the uncomfortable truth. The LLM isn't your knowledge system, it's your reasoning engine. The knowledge system needs to exist underneath it. The 3-layer AI agent. Think about it this way. Layer 1, reality. Your databases, APIs, files, events, this is what's actually happening. Layer 2, memory, your graph and vector systems, this is your machine-readable model of the world. Layer 3, reasoning, the LLM. This is where the agent interprets the situation and decides what to do. And when you connect these three properly, you get something much more powerful than a chatbot. You get an agent with current information relationships, historical context, semantic understanding, and potentially, the ability to act. Yes, the next big problem. But there's a catch, and this is where things get really interesting. What happens when the graph is wrong? Because real time doesn't automatically mean accurate. Imagine, your database says, customer signs ABC, your CRM says, customer signs XYZ, your API says, account suspended, your PDF says, account active, and now your AI agent has conflicting information. What should it believe? This is where the next generation of knowledge graphs needs something much more sophisticated. Provenance. Every piece of knowledge needs to answer, where did this come from? When was it updated? How reliable is it? What source produced it? What changed? Now your graph isn't just customer, account, it's more like customer, account, source, CRM, updated, 2 minutes ago, confidence, high. That's a much more trustworthy foundation for AI. On the start. And that changes the AI agent, because now the agent can reason not only over what is true but potentially how confident we are that it's true. That's huge, because the future AI agent shouldn't simply say, here's the answer. It should be able to internally reason. I have 3 sources, 2 agree, 1 is 6 hours old. The API is the newest authoritative source. That's much closer to how a serious intelligent system should operate. Sure, the bigger vision, so let's zoom out. Today most AI applications are built around prompt, retrieve, answer. But the next generation is moving toward observe, update, understand, reason, act. And that's a completely different architecture. Your database changes, your API changes, a new document appears, a sensor sends an event, a customer changes something, a transaction occurs, the knowledge graph updates, the AI agent sees the new state, and then it decides what to do. That's not a chatbot. That's an AI system with a continuously updated model of its environment. It's your final takeaway. So if you remember only one thing from this video, remember this. RAG gives an AI access to information. GraphRAG gives it relationships. Real-time knowledge graphs give it a continuously changing model of the world. And when you connect that to an agent, you get something much more interesting. An AI that doesn't just answer, what do I know, but can reason. What's happening right now? How is it connected to everything else, and what should I do about it? And honestly, that's where AI agents start becoming genuinely useful, because intelligence isn't just having more information, it's having the right information, the right relationships at the right moment, and the companies that figure out how to build that reliably may have a much bigger advantage than the companies simply building another chatbot. The future isn't a static knowledge base, it's a living knowledge graph feeding an AI agent in real time, and that's the architecture I'd be watching very closely.